Welcome back. In the second part of this section, we'll be looking at rationalizing denominators, and we'll also be looking at rational exponents. First off, to rationalize a denominator means to make a denominator not have any radicals inside of it at all. So there's two different scenarios that we need to consider here. One of them is the easier scenario, which is the what happens if our denominator only has a single term. So, for example, this root of 6 plus root of 7 over root of 8, the denominator only has a single term in it, and to make that no longer have a root, it's easy enough to do just simply by multiplying the numerator and the denominator by our root. And the reason why that'll turn out just nicely for us is in the denominator, we'll have root of 8 times root of 8, which is root of 8 times 8, root of 64, and root of 64 is just 8. Of course, you could also think of that as squaring 8 and then square rooting it, because of course that's square root of 8 squared. And that also, again, gives you just 8. For the numerator, I'll have to remember, and you'll notice here I'm going to draw brackets around my numerator. I'll have to remember that everybody in the numerator is going to be multiplied by that square root of 8. So I'll have root of 6 times root of 8, which is root of 48. And I'll have root of 7 times root of 8, which is root of 56. And so, of course, we are not finished yet, because now we need to look at these two roots and ask ourselves if there's any perfect squares that go into them. For 48, yes, for sure there is. If we're looking at our list of perfect squares, 4, 9, 16, 25, 36, and so on, we always want to find what is the biggest root that we can take out. So although 4 does go into 48, and it goes in 12 times, we can actually take out a bigger root, and that is 16. 16 is a perfect square, and it goes into 48 3 times. For 56, we can see that 4 goes into 56 and it goes in 14 times, and 4 is the biggest perfect square that we've got that will go into it. And so now, when I simplify the numerator, I can say that I've got square root of 16, which is 4 times root of 3. I've got square root of 4, which is 2 times root of 14, and then all divided by 8. One thing I also notice here now, if we're looking at the whole number parts, both the numerator and the denominator, all those whole numbers are all divisible by 2. So what I could do to do one little further round of simplification is to divide everybody top and bottom by 2. 4 divided by 2 is 2. 2 divided by 2 is 1, so I'd have 1 root of 14, or just root of 14. And then 8 divided by 2 is 4. Of course, this is as far as I can go. I can't combine the two roots because root of 3 and root of 4 are two different roots. Root of 3 doesn't have any perfect squares that go into it. Root of 14 doesn't have any perfect squares that can go into it. And so that's as far as we can go. You might be thinking, just as a little side note, you might be thinking about trying to do something involving the 2 and the 4, trying to somehow cancel those. But remember that to do any sort of cancellation, the reason why we were able to cancel everybody, a factor of 2 out of everybody, was because all of the terms in the numerator and all of the terms in the denominator had 2 as a factor. Unfortunately, for what we've currently got, 2 goes into the denominator, but 2 does not go into the entire numerator. It goes into part of the numerator, but not the other part. And so since 2 doesn't go into everybody, then 2 cannot be canceled out of everybody. That means that this 2 and this 4 do not cancel. So we've gone as far as we can go, and we've simplified as much as we can get. And our rationalized denominator is here. Now, if we've got a two-term expression, then what we just did will not work. Just multiplying top and bottom by a single root will not fix your problem. Instead, what we're going to use is the difference of squares identity, and that is if we have two things that are conjugates of each other. By conjugates, it means that they're the same except for the sign. So a minus b and a plus b, those are conjugates of each other. If you multiply those together, you will get one perfect square minus another perfect square. That's our difference of squares identity. So the plan here is if we have a two-term expression in our denominator, we'll multiply top and bottom by whatever the conjugate of the denominator is. So for example, if your denominator was 2 minus root of 5, you'd multiply top and bottom by 2 plus root of 5. If your denominator was root 5 plus root of 6, you'd multiply top and bottom by root 5 minus root of 6. Whatever the denominator is, multiply top and bottom by the conjugate. The difference of squares identity will mean that after you've done that, the denominator will be something of that form, something minus something times same something plus same something. That'll give you one perfect square minus another perfect square. That will get rid of your square roots that you have in the denominator. Okay, so we're going to, for this one, rationalize our denominator and then simplify. So first off, we have root of 6 minus 3 root of 2. So we're going to multiply top and bottom by the conjugate, root of 6 plus 3 root of 2. And of course, once we do that, we'll need to do a bunch of work to simplify. I'm going to start off by dealing with my denominator. I know that since I've got one thing multiplied by its conjugate, that the difference of squares identity tells me that I'm going to get the first thing squared minus the second thing squared. So that means that I'm going to eventually have no more square roots left in my denominator. For my numerator, this is kind of similar to an example that we did earlier. I'm going to need to remember that everybody in the numerator is going to need to multiply onto that root of 10. So the root of 10 will need to multiply against the root of 6 as well as against the 3 root of 2. So for the numerator, I'd have root of 10 times root of 6, which is root of 60. I would have plus 3 root of 2 times root of 10. So again, keeping the whole number parts together and multiplying the root parts together, that would give me 3 root of 20. Okay, so just a little bit of work to do to clean this up further. First, I'll deal with the denominator. So we have first term is root of 6 squared, and the root and the squaring will cancel each other out, leaving me with just 6. For the second term, I've got a 3 root of 2 that's being squared, which means the 3 will be squared to give me 9, and the root of 2 will be squared to give me 2. So for that second term, I'll actually have 9 times 2. I'll have 18. For the numerator, there's some other work that still needs to be done. So for the numerator, you can see I've got a root of 60, which again, there's a perfect square that goes into that, namely 4. 4 goes into 60 15 times. And same thing with 20, there's a perfect square that goes into that. Again, it's also 4. 4 goes into 20 5 times. So when we simplify our numerator, we'll have root of 4, which is 2, times root of 15. We'll have 3 times root of 2, which is 6, times root of 5. So notice here that when I took that square root of 4 and took it as outside of my root and turned it into a 2, it multiplied together against that 3 to give me 6. So 3 times root of 4, that's where the 6 came from, because root of 4 is 2, and so 3 times 2 gives me 6, so I'm left with 6 root of 5. The last thing for me to do here is just to finish things off. I'll leave the numerator alone for now. I've got 2 root of 15 plus 6 root of 5 And I have in the denominator root of 6 minus, 6 minus 18, which is negative 12. So one last little thing that I can do, I notice that everybody, the 2, the 6, the 12, they're all divisible by 2. So what I can do as my final act here is to divide everybody top and bottom by 2. So I'd have root of 15, I would have 3 root of 5, and I would have negative 6. This could be rewritten in a bunch of different ways. So here I have negative in the bottom. I could multiply top and bottom of this fraction by a negative 1. So in other words, I could make the bottom a positive 6 and make everybody in the numerator negative instead. So just be aware of that for any sort of expression that you have, there might be multiple different ways it could be written. So both of these are acceptable answers. I'd be fine with the first way of writing it. I'd also be fine with the second way of writing it. It's good to know. So if you were dealing with a textbook practice question and you came up with the first answer and they wrote it the second way, it's good to know that those two things are equivalent. Okay, so now talking about exponents that are fractional. So good to know if really a fractional exponent is just a kind of a root. When we're talking about a cube root or a fifth root or a sixth root, we can write that as a power where the power is a fraction. So something like an nth root, that is something raised to the power of 1 over n. And if you have a fraction that's not just 1 over something, then it's giving you a root as well as a power to raise something to. So if you've got something raised to the power of m over n, the n is telling you you've got an nth root, and the m is telling you you're raising something to the power of m. And of course, we know that we can do that in whatever order we'd like. We can either do the nth root first and then raise to the power of m afterwards, or do the power of m first and then do the root of nth root afterwards. One little thing just to be careful about here of all of this is, and this is throughout the course, brackets are very important. They tell us a lot of information about who applies to what. So for example, if we're talking about exponents, if we have no brackets, then the exponent only applies to the thing it directly touches. So for example, negative 4 to the power of 1/2, since there's no brackets around the negative and the 4, then the power only attaches to the 4, which means it's really the negative of square root of 4. And since square root of 4 is 2, then we'd have negative 2, and then there we go. On the other hand, if you had a negative 4 in brackets raised to the power of 1/2, then that negative and the 4 are inside of our root. So we'd have root of negative 4, and that's not a real number. So it is important. Brackets are important, and we do need to be careful and note that they're there. Same thing is also true when we're talking about expressions involving variables. So if we had xy to the half, if there were no brackets, then that power of 1/2 is only on the y. So if you wrote it as a root, then it would be x root of y. If you had everybody inside brackets raised to the power of 1/2, then everybody would be inside that root. Okay, so we'll do a little bit of work here to simplify some expressions with fractional exponents. Of course, these we could all do with our calculator if we wanted to, but I'm going to do these by hand just so that we can have a nice little example of doing a little bit of calculations with fractional exponents. So to start with, if we have 4 to the power of 5/2, the halves is telling us that it's a square root, and the 5 is telling us it's a power of 5. So we could either say it's 4 to the power of 5 that's been square rooted, or we could say it's square root of 4 raised to the power of 5. You could do whichever you choose, but of course, if you're thinking about which is the easier of the two options, I feel like the first option is probably not so easy, because if you raise 4 to a power of 5, that'll be a fairly large number, and then good luck taking square root of that. Hopefully it's a nice perfect square. On the other hand, square root of 5 is square root of 4 is easy enough for us to find, and then raising that square root of 4 to the power of 5 will be easier to do. Same thing with the 27. We have 27 to the power of 2/3. We can take our cube root first of 27 or take it later. If we take it first, that'll probably be easiest because I already know what the cube root of 27 is. I have no idea what 27 squared is, so I feel like leaving the squaring until later is a better idea. So away we go. Square root of 4, that's just 2. And cube root of 27, that is 3, because 3 times 3 times 3 is 27. And so I've got 2 to the power of 5 minus 3 squared. And then now all I need to do is a little bit of quick calculations. 2 to the power of 5 is 32, and 3 squared is 9, and so 32 minus 9, that is 23. All right, one more to do. And so here we've got a fractional exponent that's also negative. So first thing I suppose that I would like to do here is to rewrite this with positive exponents. So by doing that, I'll have to flip my fraction. So instead of 27 over 64, it'll be 64 over 27. It's only the fraction that's being flipped, not the exponent. So the exponent will still be 4/3. It'll just be 4/3 that's now positive. And of course, I know that when you have a fraction raised to a power, then the top is raised to that power and the bottom is also raised to that power. So I've got really 64 to the 4/3 over 27 to the 4/3. And then same as before, the thirds is telling us that we're taking a cube root. And then the power of 4 will do that after. Same thing for the 27. I'll take the cube root of that first, and then I'll raise that to the power of 4 afterwards. Okay, last little act to do here. Cube root of 64. I know that 4 times 4 times 4 is 64, so 64 cube rooted should be 4. So I've got 4 to the power of 4. And cube root of 27, that is 3, because 3 times 3 times 3 is 27. So I've got 3 to the power of 4. And so I just have to finish that off by saying, well, 4 to the power of 4 is 256. 4 times 4 times 4 times 4. And 3 to the power of 4, that is 3 times 3 times 3 times 3, or 81. So 27/64 to the negative 4/3 is 256 over 81.